Okay, I'm back with yet another circuit, and this circuit right here is called an 18-bit homemade read-only memory chip. And I'll explain why I made it, and I will explain the function. Now, I'm not sure if you can see this, but on the top here I have 12-volt supply that supplies these resistors, all coming down on their separate lines. First one designated line A, second one line B, and the third one line C. Lines A and B and C are your data output lines. Okay. You'll see that there's 3 data lines, and these lines going across right here are your address lines. And there are 6 address lines. 1, 2, 3, 4, 5, 6. Each address line is tied to the collector of a transistor. There's a resistor at the base of each one, and the first one on the bottom is number 1 all the way up to number 6. Now, the reason I built this is because I wanted to have a specific sequence of data coming out for each signal that I applied to the transistor. The way to do that is basically create a crosshatch pattern the way I did here. 3 lines. You can add as many lines as you want, actually, the data lines, and you can add as many address lines as you want too, but for my purpose I just needed 3 by 6, which is 18 in total. This is why it's called an 18-bit read-only memory. Now you'll see between the data lines and the address lines I put a diode, okay, with cathodes all facing the transistor. The reason for that is because if the transistors are all off, that means all the collectors are floating. With a constant 12 volts feeding each data line, the output of ABC are all high. They're all high, 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 okay? The way to get data coming out of ABC is to actually short out whichever line is required to be shorted out. That's what the diodes and the transistors do. So, you can see here from the table, I have a graph that shows 6, 5, 4, 3, 2, 1, which are the inputs of the transistor, right here. And on the other side, ABC, which is the output of the data lines. Now you can see from the graph here that if I turn on the transistor number 1 transistor is the only one that has a high on it. All the other ones are off. Then the output of ABC will be high, low, and low. Why is it going to be high, low, and low? Because if you look at line number 1, transistor number 1, you'll see that there's no diode between the B plus line and the collector, which will be grounded, but there is a diode on the second line and a diode on the third line. That means that when you turn that transistor on, the collector gets grounded through the emitter, so this line is sitting at ground, or negative. But this first line is still at battery voltage, because it's not tied to the collector. So this line remains high from the supply coming from the 12 volts. The second line will go down to 0.6 volts, which is the diode drop, because the cathode gets grounded through the collector, which means it pulls the anode side down to the ground side with a diode drop. So this drops from 12 volts down to 0.6, which is considered low in digital. And the third line is the same thing. This 12 volts gets pulled down to the collector, which also drops to 6. That's why you would have a high, low, and low. Okay? Now, if I was to turn that transistor off and turn the second one on, then this line gets grounded only. Since there is a diode between the first data line and ground and the third data line and ground, the second line, there's nothing there. The data output becomes what you see here, low, high, low. So you can see how this is working. So wherever there are diodes between the data lines, the live data lines with the collector of the transistor will designate what the output is going to be, assuming which transistor gets turned on. Okay, for example, up here, number 6, if I turn number 6 on with all the other ones off, the only line that will get grounded is the third line, because there's one diode going right across to the collector. The other two are open. So that means that the output will be high, high, and this one will be low, which is what's showing here, high, high, and low, because the 6th transistor is on, you see? Now, I did this for a purpose, because I needed a tester for my transistor tester that I built. And these high-low conditions are the proper sequence to check NPN and PNP transistors. The reason I have this is because, well, let me go through it. A high, low, and low will represent a high on the base, a low on the emitter, and low on the collector, because for an NPN transistor, this would be forward biased. Okay? This would also be forward biased for an NPN, and this would also be forward biased for an NPN. Now, the reason they're all in different locations is because this system is acting as a rotary switch to a transistor. Once it checks the NPN, it'll switch positions and check for PNP. Now, the low, high, and high is a forward bias for a PNP transistor, because the diodes in the transistor are cathodes together to the base. The high, low, high is also correct orientation for PNP, and a high, high, low is also correct for orientation for a PNP. So basically what this system does is you can connect any transistor in any orientation at ABC, base, collector, emitter, collector, base, emitter, emitter, collector, base, whatever, it doesn't matter. As soon as the transistors switch one at a time, it will find the correct high-low combinations on these outputs in order to cause the transistor to conduct. When it conducts, I will show you the circuit in a minute, but when it conducts, there are reverse back-to-back diodes, alternate diodes connected in each line, green and reds. When it conducts, the appropriate LEDs will come on and shows you which one is the base, emitter, and collector, okay? Or actually, it just shows you which one is the base. A green LED will come on if it finds the base, and a red LED will come on if it finds a base for a PNP. The green LED comes on if it finds a base for an NPN. Now, this is the explanation of the circuit. Basically, this is an 18-bit read-only memory chip, homemade using discrete components. Okay, I used 3 resistors on the 12-volt line to power each line. I used 6 resistors, 6 transistors for the address lines, and I used the appropriate diodes in the location necessary to acquire the data output that I needed each time the transistor is switching. Now, you can do this manually, but what I have is, I'm just showing here the ROM circuit that I built, but what I have is I have the inputs actually going to a multiplexing chip through a clock. And the clock will cause each pulse from the clock will cause the multiplexing chip to switch outputs. And so it basically starts counting from the first one up to the 6th one, then it goes back to the first one up to the 6th one. So basically it just keeps going around and around. And each time it goes around, it'll switch the outputs to these different states, okay? And depending on what positions you have the transistor, it'll turn on the appropriate LEDs. Now, this is the circuit, and I am now going to show you the unit that I put together. Very crude, okay? So let's go over here. And this is the circuit right here. Now, you can see here that from the diagram, you can see here that this is my positive input, this is my negative, going to all the emitters of these transistors. There are 6 transistors here, 1, 2, 3, 4, 5, 6. I'm not sure if you can see that. And of course, I still need to add the base resistors right across here, and these copper lines going across that way are coming directly from the collectors of each one. These copper lines going down this way are being powered by each 1K resistor feeding a common supply line. So the 1K voltage, or sorry, the 12 volts is coming down each line and going out to a combination LED, red, green, and that's actually green. It's a clear LED, but the color is green, and green red. Okay. And then these lines here go out to my transistor under test right there. Now, this is exactly as I explained in my circuit. I'm sorry for that. Now you can see here that I have, let me just turn this around a little bit. You can see there the diodes that I have from the top rail to the bottom rails which connect to the collectors of the transistor. Now, you can see here that I have one diode and another diode on this line and on this line connecting the common collector line right there for that number 1 transistor. On the second one I have a diode from this line to the collector, and I have a diode from the first line to the collector. So the first transistor will produce a high, low, low. The second one will produce a low, high, low. The third one will produce a low, low, high. The fourth one will produce a low, high, and high. The fifth one will produce a high, low, high. And the sixth one will produce a high, high, low. There you go. And all these combinations go out through the LEDs. Now, once the appropriate signals come out to bias the transistor here in the correct orientation, the appropriate LEDs will come on. So let's say that this transistor is NPN, and let's say that the red is the base lead. Okay. Now if you go to this side, you see that the red is over here. So the only time that this will come on is when the data output that comes out would be high, low, and low, which is transistor number 1, because transistor number 1 will power these lines exactly that, high, low, and low. So the high coming from this line will go through the green LED, because the green LED is forward biased to the supply line, goes out through the base, it comes back on the base on the green line right there, which powers the red LED. You can't see it there, it's right there. That red LED is reverse biased to the supply, but it's actually forward biased to the conduction between base and emitter, because that collector gets grounded. So this line is no longer at 5 volts, it's actually at 0 volts, or 0.6 volts because of the diode drop. But 0.6 volts and 12 volts means, or 5 volts means, that the base emitter junction is forward biased in the transistor. So the green LED will come on to show you the base, the red LED comes on to show you that it's conducting between base emitter, and then this other green will also come on to show you that it's conducting between base collector, because this line is also grounded. So basically what you'll get is you'll get one green, one red, and one red. Sorry, I made a mistake there. So one green, one red, and one red. When you get only one of each color, that color will tell you which lead here at the transistor is the base. So let's say you didn't know which one the base was, and you connected it, and all of a sudden the circuit scans and it turns on this green one, this red one, and this red one. So what you have is you have 2 reds and 1 green. Well, that green is the only green, because you have 2 reds coming on. So that green tells you that that's the base of the transistor, and if you follow the color code, that would be the green wire. So this green wire up here would be the base, you see. Now similar for PNP. PNP is reverse. PNP, what you'll get is you'll get one red and two greens coming on. Okay, whichever greens will come on, but you'll only get one of these reds coming on. If you get one red, the red tells you which one is the base on a PNP transistor. So the circuit actually works very good. It doesn't use any frequency generation, so there's nothing to worry about as far as frequency drift or decoupling or anything like that. This is straightforward switching that puts automatic data in the correct positions one at a time, and it will only conduct the LEDs until the correct orientation is found at the transistor. So it's a perfect transistor tester. Now, of course, the only thing it doesn't do is it doesn't tell you which one is the collector emitter, but it sure tells you which one is the base, and it also tells you what it is, an NPN or PNP. So this is a fast go, no-go test for a transistor. Of course, like I said, I still have to add the resistors right across here, okay, and then connect it to a multiplexing switch, multiplexer IC that will automatically turn these transistors on one at a time, and then recycle. So it would be a constant scanning. Okay, but the chips themselves don't have to do anything. I suppose you could program a PIC chip to do the same thing, or another, I suppose you can use logic to do what I've done, but I like doing this kind of stuff. And also, if anything should go wrong with these diodes, this is one read-only memory that you can absolutely fix instead of throwing it away or have it reprogrammed. Because if the transistors go bad, you just replace them. If the diodes go bad, you just replace them. If the resistors burn out, you replace them. And if the LEDs burn out, you replace them. So there you go. This is a homemade read-only memory, 18-bit, because you have 3 lines by 6 lines, so that gives you a total of 18. And of course, you can keep adding the address lines, as many address lines as you want, up to millions of them. And you can also add as many data lines as you want, millions of them. So you can make a read-only memory like this in any combination that you want. Okay, but this is how read-only memories work. In read-only memory chips, the diodes represent a permanently fixed data position. Okay, it cannot be changed, because in order to change it, you would physically have to do what I would do here is to remove a diode and put it in a different location, and that will actually change the data sequence. But for my purpose, what I needed it for was for this, because I needed this sequence right here, high, low, 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 high, low, and so on. These 3 right here will check NPN, and these 3 right here will check PNP. Okay? So, another circuit for your books. If you guys are interested, you can put this together certainly and try it. And if you can elaborate on anything better, I mean, being homemade, certainly let me know about it. I know this is most people will consider this a waste of time, because I could easily do this on a chip, but you know what, it's my hobby. I like doing this electronics. I like doing this kind of stuff. I'd like to know, I hate it when a manufacturer makes a chip and you don't really know what's inside. This is a chip that actually shows you what is inside. Okay, so there you go. Have fun.